So let's start by determining the mass flow rate of smoke out of the room of fire origin. Now it could be argued that there is a simple plume in the room of fire origin, and that under stabilised conditions the smoke that leaves the room of origin must be equal to the amount of smoke being produced in the simple plume. This is done sometimes, but it's probably not the most accurate way of determining the amount of smoke out of the opening. So there are more accurate means of determining the mass flow rate of smoke out of the opening, and the use of one of these more specific methods is recommended. The first model we shall look at for this is shown here. As you can see, this is a fairly simple model with only three variables: QP, the convective heat output of the fire in kilowatts; WO, the width of the opening from the room of origin; and HO, the height of the opening. This model is presented by Technical Memorandum 19, 1995, issued by the Chartered Institute of Building Service Engineers, and by PD 7974 Part 2. So what do we use for the dimensions of the opening, WO and HO? If the opening is a door in a fire-resisting wall, whether it's a traditional wall or a screen of fire-resisting glass, then the dimensions are simply the dimensions of the doorway with the door fully open. If the opening is a door in a glass shop front, then it's not quite so simple. Glass shop fronts are seldom fire-resisting, and it's generally assumed that the glass would break at some stage during a significant fire. The dimensions of the opening at the shop front, therefore, are the dimensions of the whole glass shop front and not just the dimensions of the doorway or of the everyday opening into the shop. The opening should be measured from the floor up to some structural member above the opening that would be expected to remain in situ during a significant fire, and the width is usually taken to be the entire shop front width. It should be borne in mind that there might be a case for safely assuming that the whole shop front glass might not break in a fire, and that the opening might be smaller than if it did. This might be the case, for example, if there is a very long shop front opening onto a mall, and a fire that is controlled in its extent by sprinklers is very unlikely to break glass panels that are located some distance away from the fire. There may be other variables involved in making a decision like this, and it is something that has to be assessed on a case-by-case basis. Returning to our equation, if we insert the design fire size in kilowatts, the width of the opening in metres, and the height of the opening also in metres, then we get a figure for the likely amount of smoke to emerge from the opening given in kilograms per second. For example, a 5,000 kilowatt fire in a shop that has an opening 2.2 metres high and 5.5 metres wide gives a predicted smoke output of 10.5 kilograms per second, as shown here. Let's do another example. Supposing we had a 7,000 kilowatt fire in a shop that has an opening of 3.4 metres high and 6.7 metres wide. This will give a predicted smoke output of 20.9 kilograms per second. The result of using this model for the smoke output through the opening can be taken forward as an input for subsequent models for determining the mass flow rate of smoke into the reservoir. But before we do this, we shall have a look at two other models for determining the amount of smoke that will leave an opening from the room of fire origin.